Yeah, then probably. I got it.
Slowly. Procrastination. And I just wanted to raise my hand. That makes sense. It's going in his mailbox order.
The price on it. And, maybe that's maybe on the score. Well, actually,
Okay, so this will be the last stage of my version. Maybe. But it became clear that there were some remarks that should be made about what's going on with this perturbation operation and this uniqueness statement. So a couple more things that I say. All right, so far we kind of have, I drew some pictures and described geometrically what's happening when we perturb, which we can think of as this karate chop that splits a trivial patch into two patches, and then also increases the bridge number on the spine. And then we, from that description, we sort of saw what this looks like from a triplane point of view, where we were kind of had this band inside a trivial disc and we were surgerying the disc to get two new ones. So I think the first thing I want to do is describe what stabilization or perturbation looks like from a shadow diagram point of view. So a bridge trisection is, I guess, I perturbed. There is a shadow diagram such that has two properties. First is that there's a I guess this can always be the case, but there's a simple closed curve, say delta, inside the union of the I shadows with the I plus 1 shadows. So we can think of this, let's think of it like this. So maybe this is our cycle delta. And then the second, so this would be delta. And what is happening here, we don't really know. These things kind of go off, see more about that. And maybe there's even some sort of things that cross through like this. And then the second condition is that there is a shadow Y star inside the third set of arcs, such that Y intersect delta is a point that's contained in the boundary of Y. Okay, so what I mean by that is we have an arc
Y star. Is that Y?
Oh, did I call it star? Thank you. So we have an arc Y star that looks like this, whose interior doesn't intersect the polygon over here. And then, so it does something over here, but I'll just draw it this way. Something like this. So the other end of Y, I guess, yeah.
Like one of those red arcs you just drew, your hexagon on the right. could in principle come and crash through the blue arcs. I mean, red can intersect the blues in delta, right? And blues can intersect the reds in delta.
That's right. Sorry, reds can intersect the blues and delta.
Could there be some reds cutting across that diamond on the left?
Some reds.
Nothing in your red rules that.
Well, yeah, I guess there could. I don't see that as being
That's not a problem. Okay.
Yeah. I think that's fine. And then the other thing I was wondering about was, well, let me draw this other picture. So I sort of did this backwards. If we looked instead of this piece first, what we would see is the arc. So last time we had this arc, which we called omega, right? So to do a perturbation, we want an arc omega that's embedded in one of these trivial disks. So that's what we're seeing in this picture. So this would be the result of the perturbation. And the lemma says that there exists, or that the bridge trisection is perturbed if we see sort of this left half of the result. Namely, we would see this, this polygon here connected with an arc that doesn't intersect it. Okay. All right, so this,
What if on the right, red and blue were switched? Oh, it couldn't be. It couldn't be because then you'd have you wouldn't have a region that was red. Is that right?
it could be. This then just wouldn't be.
On the right, on the top. If that hexagon, you switch all reds for blues.
Yeah, if you flip this.
Is that, or is that not even legitimate?
No, you could have that. When you deperturb, they would just cross them.
I see.
Yeah.
Oh yeah, of course.
Yeah. So to do the deperturbation, you just resolve blue across here and red across here, and then I guess I've then exaggerated them back up into this position. Okay. Okay. Any questions on this? Any other questions?
So you resolve by like twists.
Yeah, it would be like, it would sort of be like a twisted band in that case. Well, I mean, you have to be a little careful because the blue arcs and the red arcs like leave the plane in different directions. So, you know, in this case, you would, if you wanted to make this sort of recover the height, you would sort of just flip it up like this. Whereas if it was switched when you recover the height, you would sort of flip it like that. So yeah, it's a little bit like a twisted band, although it's still a coherent band. It's, it can still be a coherent band. I mean, locally, I could even just move these arcs so that it look like that, right?
Yeah.
I could just isotope this arc here and this arc here, and then it would be backwards. So I don't think there's anything too serious going on right now. Okay, so let's say that, let's make this a little more precise. Let's say that, let's say the perturbation as type n if the length of delta is 2n. In other words, if delta is a 2n gun. Let's say that that's And this is a little symmetric because as soon as we have the polygon here, we also have the polygon over here. So maybe I'm really taking, maybe this is really the minimum among the two polygons that are connected. So what I want to say now is that okay. An I perturbation type 1 is a connected sum with a two-bridge trisected anodic sphere. Okay, so let's see how this works. So let's look at this from the connected sum perspective. So let me draw a shadow diagram for my two-bridge trisection of the anodic sphere. That's a shadow diagram for one of the two-bridge guys that I drew a while back. And let's say this is a local piece of my surface S. Okay, so I want to do the connected sum of these two bridge trisected surfaces. So this is an S2. I want to do a connected sum at this point. And if we do that, what we see is, you basically just resolve these arcs across a ball neighborhood of these bridge points. So what we see is something like this. We're left with these 3 points. And so this would maybe do something like this. Something like this. And so this is what the connected sum operation looks like. Now, how do we see this as a one perturbation? Well, we have this two gone here, which has a disjoint green arc coming from it. So we can one deperturb, or maybe we'll do it like this. This is a one perturbation. And then the result of that is just, we delete this. I guess it sort of looks like this. We're just going to be left with this point way over here. And this is then just our surface S. So it sort of just moved this bit of S through to the right side of the figure. But this is the only perturbation, well, the only type of a perturbation that can be written as a connected sum. So the other perturbations are not. Okay, so I guess that I can give an example of this. So let's do it. Let's look at something that's type 2 perturb. This, by the way, this like language and notation is a little ad hoc, but
particularly the one on the left is both type 2 and type 3.
Yeah, so I would right. So it's a little vague. I mean,
That's fine.
but I would say it's the minimum. Yeah, because if this were if this happened to be a 10 gone and this was a bigone, then it would be a connected sum. So it is symmetric in that sense. So let's draw this picture here. I don't think I drew this earlier. Okay, so this is a 4-2 shadow diagram. of the unknown two sphere. And so this, I think is, so this is the graph that's a cube, I think. This is a graph of it, that's a cube. So the graph,
Yeah.
I think that's right. So the graph itself is cannot be split as a connected sum in the sense of connected summing tricolor graphs. So this is not a connected sum, but you know, there are many two perturbations. So take this bygone and any of the green arcs, or this square and any of the green arcs. And that would be a that would give the existence of a 2D perturbation. Sorry, a type 2 1D perturbation. Yeah. Okay. All right, so that's the basis for thinking about perturbation and deperturbation from a shadow diagram perspective. Does anybody have any questions about that? No? Okay, cool. All right, so now I think I just want to make some remarks about the proof of the theorem that said any two. So maybe I'll rewrite it. Any two group trisections for a given surface length become isotopic after a finite number of perturbations and deperturbations. Okay, but of course, I mean, is it clear how this is written that they might come in a mixed order?
Vicky, like, you should say in triplane moves, right? Like become isomorphic as bridge trisection.
Well, yeah, that's a good question. If I was, I don't need to consider triplane moves because triplane moves capture isotopy of the bridge trisection. This is not a statement about triplanes.
Okay.
It's a statement about the bridge trisections.
Oh, okay.
It is true that like this become isotopic then is where you would fill. If you were doing this diagrammatically, the become isotopic then is what you fill in with a bunch of triplanes. But I think it's well, and you'd probably need to do that throughout. But yeah, so this is just a statement about the decompositions. Okay. So how does the proof of this go? Well, the idea is that we need perturbation for banded bridge splittings. So we have this uniqueness statement for banded link diagrams that says any two banded link diagrams for the same surface can be related by a sequence of cup and cap moves, band slides, and band slips. And we would like to leverage that into the realm of bridge trisections, and the way we do that is we pass through the realm of banded bridge splittings. So the first thing to observe is that there's a sort of family of things we can do to banded bridge splittings.
If you consider only balanced perturbations, can you only go up?
So if I wanted this to say any two balanced bridge trisections for a surface length become isotopic after a finite number of balanced perturbations and deperturbations. No, I don't think so. We'll see. Once I get some stuff on the board, I think it'll be a little bit more clear what kind of problems we have. So I'm going to draw my banded links like this. So the first move we have is this cup move. So let's do this. And there's no bands in this picture. So the other thing I'm going to just draw, since we usually get the green tangle from the blue tangle by resolving things, I'll draw the green tangle here. So here are the green, and then in this picture we pick up a band, which I can make green. And so in particular, what do we see here? Do I want to, well, note then that the green one would pair with the blue. So this is a cut move realized within a banded bridge splitting. And we see that this corresponds to, in the bridge trisection, this corresponds to a one perturbation of type 1. One perturbation of type 1. That's what I wanted to say. I think that's right. Okay, and then similarly, we have a cap move, which this. So again, we start with the trivial die. This time, this, and yeah, a band like that. So the green originally looked like that, but now green looks like this. And so we can just check what would it look like if I threw red on here. Well, we have an extra component here. So this is a 3 perturbation of type 1. Okay, so that's the cup and the cap move. This introduces either a minimum or a maximum. And then we have 3 other types of perturbations. So let's draw some of these. So the first one is if we perturb, so we can count them. The first one is if we just perturb the banded bridge splitting away from any bands. Okay, so we're just going to do a perturbation of the bridge splitting at a point that does not have a shadow attached to it. Okay. And so this just looks like a basic perturbation of a bridge splitting. And what do the green arcs look like? Well, the green was just the same as blue there, and green is just the same as blue here too, because there's no bands. So these blue arcs are just becoming green arcs. And if we notice, what would it look like if we had thrown blue in there? Well, we see that this is a 2 perturbation because it's adding in a new component for that of type 1. 2 perturbations. So far all the perturbations we've had are type 1 only. And we see that there's 1 in each direction. All right, let's carry on. Looks like I illustrated this one a little bit different. So this one, we might have the case, yeah, I've added a little extra information here. This one, it might be the case that we want to perturb at a point that is near a band. So for the sake of completeness, I've drawn also the bridge disk over here, just to make the picture a little bit more clear, mostly for me. So what happens when we perturb? Well, we are going to perturb like this. Okay, so that's a perturbation of the banded bridge splitting. And what is happening on the gamma, on the green tangles? Well, in this picture, since there's a band, it originally looked like that. And in this picture, it looks like this. And let's just draw in Well, let's just draw the blue ones for completeness. Oops. And over here it was a different picture. So what we see again, actually, is a two perturbation of type 1. So maybe just zoom back just to make sure what I'm doing. These are all moves that take a banded bridge splitting and give you a new banded bridge splitting. Okay. And so I'm drawing them, and I'm also drawing the third tangle to give us an idea of what's happening to the corresponding bridge trisection. Okay, so the last move then is the sort of most interesting one. Let's see if I can draw it. I drew a lot of these. I don't need quite so much. Okay, so this is very similar to the last one. Here I want to perturb at a point near a band, but this time I do it differently. So how do I do it differently? Well, when I perturb this one, the point at which I perturbed started off with a band next to it, and the new bridge disk that I created for blue did not intersect the band. In this one, I start off the same way, but now the new bridge disk that I create for blue. And in the example, what I want to imagine is that I actually have sort of a chain of bands coming off in this direction. Okay. And the reason I want to do that is because, well, the green gets rather interesting. So that's what the green looks like originally. And over here, what does the green look like? It looks like this. And so just for clarity, let's draw this with the blue in mind. Right. So here we just had some component of blue-green that I've drawn as perturbed 3 times. So let's give this a number. This is going to be, I guess maybe I call it M. Or, anyway. And then what happens afterwards is we get this picture. So we've created a new component of blue and green, but it has high bridge number. Actually, I didn't expect it. And we'll call that, maybe this is that -1. So this is a 2 perturbation of type, say, M. Okay, where I guess without loss of generality, we're assuming that the bridge index here is smaller than the rest, which it very easily could be. So this is where the more complicated perturbation operations come from. It's where at some point in the proof, we might want to stabilize or perturb the banded bridge splitting in this way rather than this way. Okay. All right, so those are the 5 sort of ways to perturb a banded bridge splitting. So let's see how these factor into the so obviously, yeah, one second. Obviously, we can see the moves on band link diagram for cup, cap, band slide, and band swim. Obviously, we've seen the cup and the cap moves can be realized, and it's fairly easy to understand how that transfers over the trisection. So what we need to do is we need to understand how you do a band slide and how you do a band swim in a banded bridge splitting. Do you have a question?
Yeah, so on the picture for number 5 on the left,
Yeah.
the rightmost band gets canceled by the left, this just to the left. What's it, is it getting canceled out?
No band, well, sorry. No bands are getting, you mean like, which band? No, I mean, in the banded bridge splitting, all that's happening is we're just perturbing.
Right.
And so which band are you thinking about?
I was just thinking, I thought when we set this up, we're thinking about the discs canceling bands, like in the trisection picture.
Yeah,
You're
so
saying that this, that
there is a band here. Yeah, so I see. So like if you were thinking about the shadow diagram, that's right. This would be a blue-green polygon of length of, with 2M edges. And there'd be a clean red arc connecting it with the rest of the diagram coming from this disk. And yeah, if you deperturb along that arc, then you get back to these pictures. Does that make sense?
I think so, yeah.
Okay, that's a good question. All right, so so first let's see how to do a band swim or a band slide. A band slide may require deperturbation. Okay, so what do I mean by that? All right. So let's suppose that we have. Let's suppose that we have the following sort of setup in our banded bridge splitting. Something like this, and our bands are, now they're going to be purple orange. Orange band here, and a purple band here. And we want to slide, let's say we want to slide purple, what do I do? Yeah, slide purple over orange. So what does that mean? That means we isotope one of the endpoints of purple along our link until it meets orange, and then we slide it across. So that means I need to kind of specify the sub-arc of the link that I want to slide it along. And that would be a good role for the color to play. So maybe it's this, maybe I'm going to slide purple down this way, and maybe it comes in here, and then maybe it comes back down, something like that, and then it ends up here. So that's the sub-arc that I'm sliding along. So what we want to do is observe two things. First of all, I don't encounter any other bands on the yellow arc. So the endpoints of these bands are adjacent on that link component. And other than that, it's a bridge splitting of an unlink. So, or of an unknotted component even. Right. The yellow is part of an unknotted component. That's right. That's right. Everything that's shown is one unknotted component. So that means I can deperturb it. Okay, it's a perturbed bridge splitting of an unknot, and so that's what I do, so that I get this picture. So basically, I can take all the complexity out of the yellow component, and this is sort of what you'd expect. Well, I mean, when you think about a band slide, you kind of think about the bands already being close. We actually have to do a little bit of work to make sure they're close. But then at this point, then we can do the slide. And the way I've thought about this is, so let's keep orange right here. And then, so to do the slide of purple, I'm actually going to slide it over, and then all the way over to this edge, which gives it a half twist, but then I'm going to undo that half twist by sliding over to here, and check that the result is something that looks like that. So I've slid it so it's on the other side. Okay. So this is what you need to do in a banded bridge splitting in order to do a handle slide that's compatible with that structure. And this requires deperturbations.
So in some sense, to me, the point is that the place where you're sliding is one-dimensional. So if stuff gets in the way.
The place where you're
you
sliding
have to
is
move
one dimension.
in, you know, what I'm using here, in splitting setting, you know, you're trying to slide two things, you got 2 dimensions freedom to move for your arc.
Oh, yeah.
You gotta
This
connect
yellow
it
arc is
when-
codimension 0 inside the link.
So it blocks.
That's true.
That's the crucial difference.
Yeah. Yeah, so the band, well, so now let's talk about band swim, which is maybe a little bit more like that case. Well, not, well, yeah. Well, why don't you revisit that thought, Dave, in 5 minutes?
Yeah.
And tell me what you think. So, a band swim, on the other hand, may require perturbations. And so what's the idea here? Let's try it slightly differently. So the idea of a band swim is something like this. So in this picture, we have our 2 bands. Let's see, what did I do over here? I did purple over orange. So let's make this orange. And purple. So if you remember when I talked about this before, what I'm really drawing is the core of the band, which determines the band with the surface frame. Now, to do a swim, what we really want to do is there's that we want to sort of isotope this a piece of this band along until, you know, so it goes around all, and then we eventually want to bring it here, and then the result will look something like this purple guy goes off, and then it goes around like that. So that's what it would sort of look like to do a surface frame. Maybe I should just draw the simple case first. This is what sort of like a surface framed band swim of the purple band through the surface swim of purple through orange. Okay. But what might happen is we might have a problem because this yellow arc a priori is a complicated move in 3 space. So if we want to make it a surface frame swim, we need to push the yellow arc down onto the bridge. So this is what we did when we were putting banded links in bridge position, right? We had these bands which were complicated. We could project their cores down. They were immersed. And the way we fixed all the immersed points was to perturb, right? So let's see. Our yellow guy. Oh, I think I need more information. This. Purple. So when we project our yellow guy like this down, we might have that there's some other band shadow, say, that it intersects. And so we can't sort of do the surface frame swim of this band with this in the way. And so we solve it as always by perturbing. So what does it look like in this case? I think we want this. So now orange goes through there. Remember, these guys are underneath. So now we've fixed one of the problems with the arc that's dictating the band slide. We've fixed one of the problems it has with the shadows of the bands, and this requires a perturbation. So what I've done here is I sort of perturbed at both the endpoints of the band, and then I sort of rolled it over the top. And now which one of these perturbations did I end up using? I guess I used the one that is type 1. Yeah, I would need to relook at our figures actually to see. Now we might be discussing this next time. Surely there was one of the figures we had to do this type of perturbation. Okay. So this is what I wanted to say about why perturbations and deperturbations might both be required, because maybe the sequence of moves to get between the band and links is do some slides, do some swims, do some slides, do some swims, do some cups, do some caps. Well, every time you do a swim, you might have to perturb, and then every time you do a slide, you might have to deep. Okay. All right, any questions about that? Nothing? All right. So I'll revisit those figures and comment briefly about where that type of perturbation shows up. But for now, let's move on to part 3 of the course. We're a little bit behind schedule, so we might go through the 3 manifolds faster than originally planned, but that's okay. So part 3 is, I guess, Hager splittings. Of 3 manifolds. All right, so my idea here, as it is currently formed, was to talk a little bit about handles in general, which I think will probably be familiar to a lot of you, but I think I'm just going to do it anyway. But we won't linger too long. Okay, so let's define what we mean by a handle. So this will help us out in this part and also in part 4 when we start talking about forms. Okay, so for n greater than or equal to 0 and 0 less than or equal to k less than or equal to n, and n-dimensional k handle H is a copy of the product dk cross dn minus k, which is of course just a way of writing an n-dimensional ball, an n cell, comma, which is attached to the boundary of a compact n manifold M via an embedding P from k minus 1 times n minus which is boundary. Oops. Actually, okay, period. So initial K handle is just saying how to attach an N cell to the boundary. Okay, and it comes loaded with all of this vocabulary, which I want to put down once and for all. So let's say that we distinguish the following submanifolds of H and we confuse them with their image under phi. So let's talk about the pieces of the handle. Okay, so the first piece is the first handle, which dk cross 0. So we take the first factor and cross with the center of the second factor, the cohort, which is 0 cross dm minus k. The attaching sphere, which is the boundary of the core, which is s of k minus 1. And the belt sphere, which is the boundary of the cohort. And then let me just say that phi is called the attaching map. And the neighborhood of the attaching sphere, given by including the full second factor, is the attaching region. Okay, so both sphere, attaching map, and attaching region. And finally, A is the index. Okay. Did I get it all right? You guys can probably all correct me if I didn't. Okay, so writing the definition is one thing. I think what's really helpful is to basically draw all of the examples. Probably you guys have done it already, but I think we're going to run out of time, and that I'm going to just make that an exercise. But let me say one more thing. Diffeomorphism, the union of M all along phi with this handle is determined by two things. First, it's determined by of the attaching sphere into the manifold. So here, instead of considering the entire attaching region, we're just going to consider the sort of, you almost want to say the core of the attaching region, but that would be not a good choice of words. Just the attaching sphere. So this embedding with trivial normal bundle. And the second piece of information is a framing half of this, this embedded sphere. E, an identification of the normal bundle U of 1 with Sk minus 1 is R minus. Okay. All right, and in my notes I say more on this later. For now, let's worry about. Let's think about n less than or equal to 3. Okay, so these framings will be more important when we talk about 4 manifolds. But for now, let's worry about the case of n equals 3. And then so your exercise for class next time is draw examples of every type of k-handle of n-dimensional k-handle with n less than equal to 3. So you can think about, you can draw the handle, and you can also think about how it's being attached to the boundary. And if you want help, then you can look in the notes because I've done that. So. Okay, so here we go.
It was an exercise last semester.
Yeah, in Dave's class. Yeah, it's a good exercise to do every semester. Was it anyone in here not in Dave's class? I figured there'd be at least something.
Don't be around.
Not to make our lovely viewers at home.